This is an overview of L'Hopital's rule. We're going to be using the OpenStax Calculus Volume 1 text, and in particular, Section 4.8. In Section 4.8, we can find this picture. We have an orange curve giving the graph of g of x, and we have a dark blue curve giving the graph of f of x. And they make a note that the linear approximation, the tangent line for f and the tangent line for g, that taking the limit of the linear approximation over the other linear approximation will approximate the limit of f and g. And with that observation, we can see that looking at the quotient of f over g can be the same computation as f prime times the difference in x's over g prime in the difference of x's. But these difference of x's go away, leaving you with f prime over g prime. All right. More formally, here is the statement of L'Hopital's rule. We'll have two statements. The case of 0 over 0, that's an indeterminate form, 0 over 0. And here is the statement, what we just saw, that the limit of a function over another function, where each function is in the limit producing 0, may be computed by taking the limit of the quotient of derivatives. Now let's look at why this is true. Here's a proof. They set up the proof. They have a bunch of different conditions, namely that the functions f and g are nice and that they each limit to 0 at a. And then the meat of the proof is here in this computation. We want to start with the limit of the quotient and arrive at the limit of the quotient of derivatives. So let's see why that is true. First, in the numerator, let's add 0. We're adding 0 by subtracting f of a. F of a and g of a are each 0. So this is just adding 0. In the top, add 0 in the bottom. So this numerator is this numerator, and this denominator is this denominator. Nice. Next, let's multiply this quotient by 1. They're saying algebra. Take 1 over x minus a, all over 1 over x minus a. That is a quotient of 1. So we're multiplying by 1. Next, this is a limit of the top quotient over the bottom quotient. That's a limit of a quotient. So by properties of limits, this is a quotient of limits. The top limit, the bottom limit. Now looking at each respective limit, here in the top, this is by definition a derivative. A derivative of what? Of f. So we get f prime, and then at what point? At a. So this top is f prime of a. This bottom is likewise taking the limit of a difference quotient gives you g prime of a. And now we undo basically what we have just done above. We say that the top is, now we're going to use the fact that f prime is continuous to say that f prime at a can be obtained by taking the limit of f prime of x. Likewise, g prime of a, using that g prime is a continuous function, is found by taking the limit of g prime as inputs x go to a. And again, this is a quotient of limits, so we can write that down as the limit of quotients. And this then proves L'Hopital's rule. It's worth opening up the book and reading through the examples. That the value of a may be infinity or negative infinity. That this limit computation will hold even if the quotient produces a positive infinity or negative infinity. So in particular here, C, the limit x goes to infinity, is identifying with a being positive infinity. Nice. The book then goes on and continues. It's shown the 0 over 0 indeterminate form case and makes note that the indeterminate form infinity over infinity may also be a case in which L'Hopital's applies. What about other cases? So the two previous theorems were for the indeterminate form 0 over 0 and infinity over infinity. Then it's a straight computation. Differentiate the top. As a separate computation, differentiate the bottom. So for these two forms, you just differentiate the top, differentiate the bottom, then compute your limit. There are other indeterminate forms like 0 times infinity. Infinity minus infinity. Infinity is not a real number, so this doesn't make sense. 1 to the power infinity. Infinity to the power 0. 0 to the power 0. These are all indeterminate forms, and they may be manipulated and return you back to the form of 0 over 0 or infinity over infinity. And then that is the key idea. That was a quick overview of L'Hopital's rule.